Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 22nd lecture. In this lecture, we will be discussing static timing analysis. So, static timing analysis is a very important component of VLSI design flow because it is used throughout the design flow and it ensures the timing safety of our circuit. So, we will be discussing static timing analysis in 4 lectures. So, in this lecture, we will be looking into the basic concepts related to static timing analysis, and in subsequent lecture, we will be looking into the mechanics of static timing analysis, meaning how static timing analysis is done, and then we will be looking at some advanced concepts related to static timing analysis, and then we will be also be looking at constraints, or meaning how we specify the required behavior for our design in terms of its timing. Now, let us look into what is done in static timing analysis. So, the most important purpose of static timing analysis is to ensure that the circuit is in a valid state at each clock cycle. Now, what is meant by valid state and how does an STA tool ensures that the circuit is in the valid state at each clock cycle? We will be looking at it in later part of this lecture. Then the second important task that is carried out by the STA tool is to ensure that the given design is capable of working at a given frequency, right. So, how do we specify frequency for an STA tool? So, we specify it in the constraints file, which is typically written in Synopsys design constraints format or SDC format, right. So, in SDC file, we as a designer, we specify that at what clock frequency our design is expected to run, and the STA tool ensures that the design can indeed work at the given frequency in the worst case, right. So, what it means is that an STA tool does not try to come up with a frequency at a design can run, right. So, this is an important thing that needs to be understood, that the purpose of STA is not to find a frequency at a design at which a design can run, but the purpose of STA is to ensure that at the given frequency it is safe to run a design, and to ensure this, that the STA tool will take pessimistic view wherever required. And the third important thing that an STA tool does is that it ensures that the setup time and hold time for all the flip flops in our design are met, right. So, in the last lecture we had looked into that for a flip flop there is a forbidden window around the clock edge where the data signal cannot change. So, an STA tool will ensure that the constraint of setup and hold time for each flip flop in a design is indeed met. And to ensure, or while performing these 3 tasks, what does STA tool does is that it takes a worst case view wherever required, right. So, it is the purpose of STA is to ensure the timing safety of our circuit, right. To ensure the timing safety, sometimes the STA tool can take a pessimistic view, right, and it can throw some unnecessary violation, but an STA tool will never suppress a real violation, right? Wherever it can throw some extra violations, but once a design is passing then STA tool, meaning that then STA tool says that where there is no timing violations, then the design is indeed safe to operate as per its timing requirement. So, while ensuring these three while performing these three tasks, the static timing analysis does not apply any test vectors, right? And in that sense, it is a static kind of analysis. It is not a dynamic timing analysis. It is not that it is applying test vector and then seeing the response and then checking whether it is timing safe or not. What the tool does is that it only, or an STA tool does is that it only concentrates or focuses on the worst case behavior of the design. And in the worst case, most of the input vectors that we can apply to our design, those do not contribute to the worst case scenario, and therefore we can safely neglect those test vectors. So the static timing analysis does analysis without using test vectors. Okay, so while doing its analysis, it considers inputs and logic 1 values at the inputs of the gates, such that the worst case scenario is automatically captured. Okay, so an STA tool ensures that the design will not have setup or hold violations for any test vector. Why? Because if it is verifying, it is taking pessimistic view throughout our design, then the one which is considered by STA will actually be a superset of whatever test vectors can be applied to our design, and therefore if the tool is able to establish the timing safety of a design for the worst scenario that it has or the pessimistic scenario that it has considered, it will automatically be timing safe for the other situations or other possible test vectors that can be applied to our design, and therefore we can say that the design is safe for any test vector, right? So we can differentiate between what is different, or so we have in the earlier lectures we have looked into another verification technique, and that was simulation, right? Now we can differentiate, or we should understand the differences between the simulation and static timing analysis. So in static timing analysis, we do not use any test vector. We assume the pessimistic view of timing everywhere, and based on that we ensure the timing safety. And in simulation, what we do is that we apply test vectors, zeros and ones at the inputs, and then see its response with respect to clock cycles, and then if we have model delay in our circuit, then we with respect to delays and so on. So for simulation, test vectors will be required. For STA, no test vector is required. And then for the STA does not check the functionality, meaning that it does not consider that if I apply 0 and a sequences of 0, whether the sequences of zeros and 1 produced at the output, that is correct or not. That purpose of STA is not to verify the functionality, right? It totally ignores the functionality details of, or Boolean function detail of the circuit, right? It only considers the timing arcs, and based on that it does the timing analysis of our circuit. While the purpose of simulation is to check the functionality, meaning that if I give a sequence of zeros and ones at the input, then whether we are getting a right sequences of zeros and ones from the circuit or not, that is what the purpose of simulation is. So here we are verifying only the timing in a static timing analysis, not verifying the functionality of our design, right? So in STA, what is the mechanism? So in STA, the analysis is performed taking pessimistic view of delays and other attributes of the design, and simulation is done based on the specified test vectors and delays. So these are some of the important differences between STA and simulation. Now, before moving further, let us understand that what is expected out of a synchronous design and what are the valid states of a synchronous design. So, let us consider this circuit. So, in this circuit there are say 2 flip-flops. For simplicity, let us assume that these flip-flops are ideal, meaning that the clock to Q delay is 0, the setup time of this flip-flop is 0 and the hold time is also 0, right. So, we are assuming that our flip-flops are ideal. And then we are saying that there are buffers in our circuit. So, there are buffers on the data path D1, D2, D3 and there are 2 buffers on the clock path C1 and C2. These buffers have some delay, right. For simplicity we have just taken a buffer, right. So, and these buffers can have delays and suppose we apply input at the port in, right. So, we are applying input at the port in and what are the inputs? The input in the first clock cycle is A, in the second clock cycle is B, then in third C and in fourth we have D, right. Typically these numbers, these input that will be coming at in will be a digital value, meaning that it will be either 0 or 1, right. But for our analysis I have represented using A, B, C, D so that we can easily understand that what is happening in our circuit. So, we have given different identifiers to signals at different clock clock cycles, right. Also assume that initial value at the point at the output of this flip flop 1 Q is P and the output value at the output of the second flip flop FF2 is Q, right. Suppose this were given initial condition and this sequence of inputs were applied at the input port in, right. Now, state is defined by the combination of values at the Q pin. Let us assume that we are defining states by the values that are there at the Q pin for these 2 flip flops. So, what is the initial state? Initially this Q pin had value P, this Q pin had value Q. So, the initial state is PQ, right. So, initial state is PQ. Now, let us understand the behavior of the circuit in different clock cycles for various cases of delay of the buffers, these buffers, right. So, now we are saying that now what will happen if this is a perfectly synchronous circuit, what will be the happening and what will be the state of the system, meaning that what will these values in different clock cycles, right. We will take different delays of D1, D2, D3, C1, C2 and C different scenarios. So, let us take the first scenario in which we say that delay of D1, D2, D3 have some finite values, but it is less than 1 clock period, right. So, D1, D2, D3 are having some delay, but less than the 1 clock period and the delays of C1 and C2 are negligible. Let us assume that delay of these two are negligible, so we can remove them from the circuit. So, equivalently we can represent the circuit like this. Now, in this case, suppose we applied the input as A, B, C, D at the input in, right. What will be the states at these clock cycles, right. What will be the value at these clock cycles at FF1Q and FF2Q, right. So, suppose what will happen is that if A was here, right, then A will come and propagate here at D pin and whenever the clock edge will come, we will get A at this point, right. So, this A will come at this point. Now, once this A comes here, it will propagate through D2 and delay of D2 is finite less than 1 clock period. So, when in the next clock edge by that time this A will reach here at the D pin and in this third clock cycle A will go to the output, right. Similarly, B will go to this and then in the next clock cycle edge it will go this and this P, whatever was P initially here, right. Here we assume that at 0 clock cycle we had P at this point. So, that will go and propagate to D, and in this clock cycle will have P. And similarly, this C will come here, right. So, we will get something like this, right. So, the value, if D1, D2 and D3 have some finite delay less than the clock period, then the value at the Q pin will be as shown in this figure, right. Then what are the valid states that will be there in for this circuit? So, valid state will be PQ, right, initial state, then AP, then BA, then CB. So, these are the valid states, right. So, these are the valid states of a synchronous circuit. This is how a synchronous circuit behaves, and these are the valid states. Now, what can go wrong in a synchronous circuit? Let us look into that. So, the first case can be that the delay of this D2 becomes very large, right. So, now let us assume that C1 and C2 are negligible, we can remove them, right, and delay of the circuit element D2 is more than 1 clock period, this is more than 1 clock period and less than 2 clock period, and D1 and D3 are minimal, they are very small delay on this, right. So, equivalently we can draw something like this. So, we have D2 which is taking more than 1 clock period, and D1 and D3 are having small delays. Now, if we apply the same stimulus at the input and input in, right, A, B, so the same thing, what do we expect, right. So, at this FF1Q, there will be no change as similar to the synchronous behavior, meaning that this is a small delay. So, whatever will be there in the next clock edge, it will be captured. So, whatever was at A, it will go to in the next clock cycle, it will go to FF1Q at this point, and then whatever was at whatever comes in the second clock cycle, it will become available in the clock, it will come at the output in the third clock cycle at FF1Q, right, and in the fourth clock cycle and so on. So, there will be no change at the output of FF1Q. But what will happen at FF2Q? At that point, what will happen is that if there was a value P here, it will propagate through D2 and it will take more than 1 clock cycle to reach the point D, right. So, it will not be captured in the next clock edge, but in the next to next clock edge, right, and therefore, it is not captured. Ideally, it should have been captured at this point, right, but instead of being captured here, it will be captured in the next to next clock cycle, right. Why? Because the delay of element D2 is more than 1 clock period, but less than 2 clock period, right. Similarly, A will be not be captured in the next clock cycle, but in the next to next clock cycle, right. So, this the values at FF2Q will get disrupted. So, the states that will now will get as PQ, right, and then AQ, BP and CA, right. So, these are the states that will be getting in our circuit, but in the last slide we saw that what are the valid state, these are AP, BA and CB for the synchronous circuit, right. So, the states that we get in our circuit are different from what we wanted as in the synchronous circuit, and therefore, the synchronicity of our design is lost. The valid states are not existing in our circuit, even though we assume that flip flops are ideal and many ideal conditions prevailed in our circuit, right. So, in effect, clock fails to capture the right data due to late arrival of the data, right, and this is known as zero clocking. We call this as a case of zero clocking. The circuit goes into an invalid states. These are invalid states, right. Why? Because it is different from the one that we expect in a synchronous circuit. Now, let us look into another scenario. In this case, what we are saying is that let the delay of D1, D2, D3, C1, all of them be very small or negligible. while the delay of this element C2 is somewhat positive and let us call it as delta. Now, in this situation, we can draw an equivalent circuit where D1, D2, D3 are very small or negligible, and then we have a delay delta amount on the for the element C2. Now, in this case, what will happen? In this case, the data that was there, say at the A that came here, in the next clock edge, it will go at this point. But when it reaches this point, the delay from this point to through D2 is very small. So, A reaches very quickly to the input of FF2D, and there is a delay on the clock path, and the clock will reach later on, right. So, what will happen is that in the second clock cycle, we will have the data in two different flip flops, right. So, same data got latched by two flip flops in the same clock cycle, right. So, this is the case. So, then the circuit goes is still on in the invalid state. So, this happened for this cycle. Similarly, it will happen for the other cycles also, right. So, the states will be PP, AA, BB, CC, right, for the for this case, and while the valid states were what we saw in the synchronous circuit, right. So, now the circuit has gone into wrong state, right. So, in effect, the data gets captured by two flip flops by the same clock edge, and therefore, we call this scenario as we have reached a double clocking scenario. Okay. So, this scenario is known as double clocking, and the circuit goes into invalid states. Okay. So, we need to avoid this. So, now what does the tool does to ensure this, that double clocking and the zero clocking does not take place, right. So, the NSTA tool avoids zero clocking by setup analysis or the late analysis. Why it is late analysis? Because it is looking into the data path and checking whether the data delay between two flip flops is not too high, or does not at the capture flip flop the data does not reach too late, so that the synchronicity of the data is lost, right. So, we avoid zero clocking by setup analysis or late analysis, and we avoid double clocking by hold analysis or early analysis. What it means is that to avoid double clocking, the tool will ensure that the data does not reach at the capture flip flop too early, so that it gets captured in the same clock cycle, right. So, that is what is checked in hold analysis or early analysis. So, a synchronous circuit can contain many flip flops. In the figure that we just saw, there were only two flip flops, right. But in a real design, there may be thousands of flip flops. Now, in that case, how does the timing constraints are checked? So, in that case, what the tool does is that it considers the constraints between pairs of synchronously adjacent flip flops. It considers flip flops pairwise, right. So, in a synchronous circuit which contains many flip flops, data can propagate sequentially through a pipeline before reaching the output. So, STA tool examines each pair of launch and capture flip flops separately, right. So, the tool will consider the path from one flip flop to the sequentially adjacent flip flop, meaning from the launch flip flop to the capture flip flop. It will consider all pairs of such combinations that are possible in the circuit. So, now there are various types of combinational gates that can be encountered in the path, right. So, we have taken a simplistic case in which we have only the buffers in our path, right. What if there are AND gate, NAND gates, XOR gates and other kinds of complicated gates? In those cases, what the tool will do is that it will add delay of the combinational circuit elements in the path and the check for the delay requirements. For example, there was an AND gate followed by NAND gate and so on, then it will add together the delay of all the circuit elements which is encountered from say Q to D, and based on that it will do ensure that the delay between Q and D is such that the synchronicity of the data design is maintained, right. So, now another important thing is that we have considered ideal flip flop, right. Now, what if our design has non-ideal flip flop, right. Typically our design will have some setup time, right. It will also have hold time, right. So, and it will also have say clock to Q delay, right. In those cases, how is the analysis done? So, in those cases, the analysis is similar to what we have done in the previous lecture. Only thing is that the constraints become more stricter. There is we need to consider the time when the signal arrives at the D pin slightly taking into the account the margins of the setup time and hold time of the flip flops also. So, it makes the verification a bit more pessimistic, yet the same analysis can be used to ensure the states of the the states of the synchronous circuit are valid, and also the flip flops that are in our design, those the constraints of setup time and hold time for those flip flops are also maintained, or those are also met. So, now let us look into the setup requirement of our that needs to be met for a realistic circuit, right. So, in setup requirement check, what is done by an STA tool is that it ensures that the data sent by the launch flip flop in any given clock cycle is captured reliably by the capture flip flop in the next clock cycle, right. And while ensuring this, the tool will also check for the setup requirement of the flip flop at the capture side. So, let us understand how does the tool does this, right. Let us consider this a part of a circuit in which this is a launch flip flop, this is the capture flip flop, and these two flip flops are synchronously adjacent, meaning that there is only combinational circuit elements in between them, right. So, let us assume that the combinational circuit element is D and its delay is T data, right. And there are two delay elements on the clock pass C1 and C2. The delay of the element C1 is T launch and the delay of the element C2 is T capture, okay. And then let us assume that the clock is generated at this clock source, and the clock to Q delay of this flip flop is T clock QL, and the setup and hold time at the capture flip flop is T setup and T hold, right. Now, understand that we are considering the setup and hold requirement at the capture flip flop, not at the launch flip flop, right. At the launch flip flop, the check is not happening. The check of timing is happening at the capture side, at the capture of the synchronous for a pair of flip flop, the check happens, the check for setup and hold time happens at the capture side of the pair of flip flops. Okay. Now, let us understand what are these constraints or requirement that must be met for this circuit. Now, the arrival time, now let us assume that a clock edge is generated at time t is equal to 0 at this point, right. Now, this clock signal will go and it will undergo a delay of t launch, right, and it will undergo and it reaches this clock input, and data will be captured, will be whatever was at D, it will be moving to Q and it will start propagating in this combinational path, right, and it will propagate and finally reach the D input. Now, when will this data reach the D input? We can add the delay and just find out, right. So, the delay will be of this element, and then the delay of the clock to Q delay of the launch flip flop, and the delay of the combinational circuit element. So, the arrival time of the signal at the D pin will be T launch plus T clock to Q delay, right. This is the clock to Q delay of FF1 and T data of the combinational circuit element, okay. And then the required time for data to settle at FF2D, when should this data should settle? So, we have seen that if there is a clock edge, right, we are not allowed to make any change in data for setup for the time that is known as T setup. For T setup duration, we cannot make change in the data. So, data should arrive before this, it cannot arrive later than this, and therefore, the required time is T period. So, now when will the next clock edge come? So, we want that the data that was launched by this clock, this flip flop 1, it should get captured in the flip flop 2 in the next clock cycle, right. Now, when will the next clock edge be generated at this point? It will be generated after one clock period, that is what T period is, right. And then it will start traversing, it will undergo a delay of T capture, right, and then it should reach, and then it reaches at this point, and data should reach T setup time before this clock edge, and therefore, the required time is T period plus T capture minus T setup, right. That is the time when we expect that the data should come before this time, right. So, we can write this constraint as T required setup is greater than T arrival, right. So, this is the arrival time, and this is what we want, that this required time should be greater than. So, the arrival time should be less than this required time. This is what the constraint of setup time, setup requirement is, right. So, we can write this now, we can just put this expression, this equation and this equation in this inequation, and we get this expression, right. So, T period plus T capture minus T setup, that is this is T required, should be greater than T launch plus T clock to Q delay plus T data. Okay. Note that clock to Q delay is considered for the launch flip flop, not for the capture flip flop. Now, we can write the same equation by moving this T capture on the other side, right. So, we get T launch minus T capture, this moves to the other side, and that is why it becomes minus T capture plus T clock to Q delay, and the other terms remains the same, right. So, what we have done is that we have moved T capture on the other side and also T setup on the other side, right. So, this gives us the constraint on the clock period, how much, what will be the minimum value of the clock period that we expect, for which this constraint will be valid, right. So, now the term T launch minus T capture defines that what is difference of the arrival time of the clock signal at this point and this point, right. This is known as the clock skew, okay, the clock skew, meaning that what is the difference in the arrival time of the signals at the clock bits. So, in terms of clock, if we denote clock skew as delta LC, L means for launch and C is for capture. So, delta L, the T period should be greater than delta LC plus T clock to Q delay at the launch flip flop, and T data, right. So, this is the T data, and T plus T setup C, that is the setup time of this capture flip flop, right. Now, what the tool will do is that the tool will pick this T period from the constraint file or SDC file where we have specified the clock frequency, right. And then these terms, this quantity will be decided by the tool based on the clock path, the attributes of the flip flop, clock to Q delay of the launch flip flop, and the setup time of the capture flip flop will be picked from the library, right. From the technology library, this information will be picked, and then T data will be computed for this for the path between Q and D. How that data will T data will be computed, we will see in the later lectures. It will just be the sum of delays encountered for each of the gates in the path, right. Now, because of many reasons, these numbers can vary, right. So, for example, due to process induced variations, the clock to Q delay and say setup time of flip flops, and also the skew of the signals, or skew of the clock signal can vary because of, say, process induced variations. And also there can be multiple paths between Q and D, right. There can be multiple paths. Now, this constraint should be valid in a circuit for the worst case scenario, and therefore, what we should do is that we should consider this data to be the max, right, because then if we take the maximum of, suppose there were 3 paths, one was having a delay of 100, other as say 200, and third one was 150. So, out of various paths, we should pick the path which has got the maximum delay of T 200. Why? Because if we take the maximum, then this constraint is most likely to fail, right. Because this is coming on the less than side, and if we take the maximum value, then it is most likely to fail, and therefore, we should take the maximum of all, or we consider maximum of all these values. Now, setup violations can occur if the clock period is decreased, right. So, if we decrease this constraint can be violated. So, if we decrease the clock period, then we are basically increasing the clock frequency. So, there will be a limit on the clock frequency at which a given design can work. Beyond that, it cannot work, right. So, if we go on decreasing the clock, increasing the clock frequency or decreasing the clock period, at some point this inequality will break, right, will get violated. Similarly, if the delay of the capture clock path is decreased, right, if the delay of the capture clock path is decreased, or the delay of the data path is increased, right, or the delay of the launch clock path is increased, then this constraint is more likely to fail. Okay. Now, let us consider a scenario in which we have ideal flip flop, right. So, suppose there was an ideal flip flop, what will happen? Instead of these flip flops, suppose these were ideal flip flops. Now, if the flip flops were ideal, then clock to Q delay will be 0, we can remove this, and setup time will be 0. So, in that case, what is the constraint? So, the constraint is T period should be greater than the clock's Q delta LC plus T data max, right. So, if the and what will happen if we have an ideal clocking structure, meaning that if the clock reaches at this point and this point at the same time, that means the clock's Q is 0, we say that this is an ideal clock. If the ideal clock, the clocking structure was 0, then this term will also vanish. So, then what the final constraint remains for the ideal case? T period is greater than T data max, right. So, now what does this constraint signify? This constraint basically signify that there is no zero clocking in our circuit, right, if that is what we discussed earlier, right. So, if we saw that zero clocking can happen only when we saw when the delay of between the two flip flops were more than one clock cycle. But this constraint says that if the delay is less than one clock cycle for the ideal situation, that is the flip flops are ideal, clocking structure is ideal, then there will be no zero clocking, right. So, this constraint basically avoids zero clocking in our circuit for the ideal case. Now, let us similarly we can compute the hold requirement, right. So, the hold check is from one active edge of the clock in the launch flip flop to the same clock edge at the capture flip flop, right. So, in what do we check in hold requirement? We check that the data that is launched by a flip flop does not get captured by the capture flip flop in the same clock cycle, right. So, it is same clock cycle, not the next clock cycle, right. So, it ensures that the hold requirement of the flip flop is also met, right. So, the circuit is the same, only thing is that instead of the setup time at the capture flip flop, we now consider the hold time. Now, what will be the arrival time of the signal at this point? It will be the same, right. So, if a clock edge is generated at this point at time 0, then it will reach here after T launch at this point, and then it will reach here after T clock to Q delay at the of launch flip flop, and then from this point to this point it will take T data or amount of delay, right. This is the arrival time at this point. Now, what will be the required time? Now, data to arrive at FF2D, right, after the required time, and that required time is T capture plus T holds. So, let us understand what this required time signifies, right. Now, there was a clock edge that was generated at time 0, right, at this clock source. Now, that same clock edge will reach this point, right, after a delay of T capture, right, T capture, right. So, this is and in for the whole requirement, we are trying to check that data is not being captured by the same clock edge. Therefore, we are not taking clock period in this case, right. So, clock period is immaterial or not and not need not be required to be considered in this case, right. Now, how does this term come? The second term T hold C, right. Now, we have seen that if there is a flip flop, there is a forbidden window. So, after the clock edge, there is a time T hold for which the data should not change, right. This is T hold, or rather T hold, right. So, this is the duration for which the data cannot change at the Q pin, right, and that at the D pin, or at the D pin we are not allowed to change. So, this is on after the clock edge, the data should remain steady for the time T hold. Now, we want that the required time is such that the data should not come before this and also within this window if it should not come, right. If it comes within this window, then we will get a hold violation, and data can come any time after this window, right, and that is why we need to add this T hold C in this, right. So, to avoid double clocking and hold time constraints of flip flop, we need to ensure that the arrival time is greater than T required, meaning that the data can come anytime after this, right, and therefore, T arrival is greater than T required hold, right. So, that is what we have computed here, right. Now, using these two equations, we can expand this inequality. So, this equation and this equation, we just put it and we get this hold requirement for these two pairs of flip flops. Now, similar to what we had done for setup analysis, we can take this T capture on the LHS and we get this delta LC, right. That is T launch minus T capture is defined as the clock skew, and we denote it as delta LC, and T clock to Q delay, right, and T data, that should the sum of this to be greater than the T hold or the hold time of the capture flip flop. Note that we are considering hold time of the capture flip flop, not of launch flip flop. Now, what will be the most restrictive requirement for this, right? So, now this inequality is more likely to fail if this number comes is very small, right. So, as we go on decreasing this, this inequality is likely to fail, right, and therefore, T data should be taken as minimum, right. So, if there are multiple paths between this, we should consider the path which has got the minimum delay for most restrictive or pessimistic analysis, right. Similarly, if due to PVT variations, if the clock skew is changing or clock to Q delay is changing or hold time is changing. So, for these two quantities, that is clock skew and the clock to Q delay, we should take the minimum value, and for the hold time we should take the maximum value, because then this constraint is most likely to fail, right. Now, hold violation can occur if delay of the data path is decreased, right. If we decrease this, it is more likely to fail, okay, or delay of the launch clock path is decreased, right. If we decrease this, right, or delay of capture path is increased. If we increase this, then this inequality is likely to break down. Now, what will happen for an ideal flip flop? Let us consider an ideal flip flop. What will be the constraint for that, right? So, for the ideal flip flop, what we can say is that for an ideal flip flop, we can say this clock to Q delay is 0 and hold time is 0, right. So, what constraint do we get? We get delta LC plus T data min should be greater than 0, right. This will be the constraint. Now, when is this constraint? When is this constraint likely to get violated, right? Typically, T data min cannot be negative, right? But delta LC, that is the skew, can be negative, because it is the difference of these two quantities, T capture and T launch and T capture, and if T capture is more, the data is likely to be, if the clock signal encounters more delay on the capture path than on the launch path, then this quantity can become negative, right. And that is what we saw when we were looking at the double clocking scenario. We made a situation in which the clock skew was negative, and as a result of this, this constraint was violated, and we assumed that this is negligible, and that is why it was violated in our case, right. So, in effect, if we assume ideal flip flop, what the hold requirement is checking, it is checking for that the design, there is no double clocking in our design, right. And other important thing that can be inferred from this equation is that there is the hold requirement strongly depends on the clock skew, right. And if during logic synthesis we have assumed, say, clock skew to be 0, typically we assume it an ideal structure, then clock skew is 0. In that case, this T data, the hold time constraint just translates to T data min is greater than 0, right. It is typically more likely to be followed, or no, or this constraint is likely to be met most of the time, because the delay will be, there will be some delay on the data path. The corner cases will be the situation in which we have kind of shift register, in which we have flip flop and then another flip flop, and there is no logic between them, a shift register kind of scenario. If there is in our design, then the whole violation is more likely to happen in those kind of situations. Another thing that we should infer is that during the logic synthesis step, it is typically not that much important to look into the hold check. Why? Because the hold check depends a lot on the clock skew, and that picture we get only when we have done clock tree synthesis or we are into the physical design. Therefore, fixing of hold time violations during the logic synthesis does not make much sense, because most of these hold violations which we see in logic synthesis will typically be will be automatically fixed because of say wire delay on the data path, and new hold violations can appear after clock tree synthesis because of the clock skew, and therefore fixing hold violations typically we postpone up till the time we have gone into the physical design, we have made the actual clocking structure, and then after that we have a better picture of hold violations, and then we fix the relevant hold violations in our design. So, if you want to look into these concepts in more detail, you can refer to this book. Now, to summarize, what we have done in this lecture is that we have looked into that why STA is needed in a design, how does STA ensures that synchronous behavior is maintained in a design by analyzing the cases for zero clocking and double clocking and throwing violations whenever it finds that there can be a situation of zero clocking or double clocking in our design. And also we looked into that how the setup constraint or requirements and hold requirements for a circuit is derived, and how those requirements ensures that the given circuit will meet the setup and hold time of each flip flop in our circuit, and we also be capable of operating at the specified clock frequency. So, in the next lecture, we will be looking into that how these constraints or these timing requirements of setup time, setup and hold time uh, and early and late analysis, how are these requirements modeled by the tool internally and then evaluated and checked. So, we will be looking into the mechanism of STA in the next lecture. Thank you very much.